So we have a few guidelines when we're using Kirchhoff's rules and applying the loop rule, because sometimes electrical devices will have a positive change in potential, and sometimes they're going to have a negative change in potential. That's going to depend upon a couple of things. First of all, what kind of device is it? And then which direction are you measuring the voltage or the potential difference across? Are you going from one side to another or from that other side to another? Let me show you. So we're going to have the direction that you're traveling in the current in the circuit, and then also the direction of the current. So let's consider these scenarios. In each, you're traveling from point A to B. So traveling, as we're going through the circuits, we will be moving here from point A to B. If that doesn't make sense to you now, don't worry. We'll see some examples, and it'll make sense to you in a little bit. So I'm moving from point A to point B in each of these. Now, I have a couple of things. First of all, that's the direction that you're traveling through the circuit. Moving across this resistor, going from A to B. Let's first consider that the current is moving also from point A to B. In this case, our resistor acts as our resistor normally does, and it has a negative change in potential. So my change in potential, or my voltage, is going to be negative IR. Now let's consider we're still moving from point A to B, but now my current is moving in this direction. All right, so we're traveling through the circuit in this direction, but we're traveling in a direction that's opposite the direction of the current. In this case, my change in potential is going to be positive IR. So notice there are two directions here that we're considering. There's the direction of the current, and then the direction that we're traveling through the circuit, that we're considering the circuit. All right? If those two are opposite, it's a positive change in potential. If they are in the same direction, it's a negative change in potential. Now, for the batteries, you only need to consider the direction that you're traveling. It doesn't matter about the current. I always like to think of like a little ramp. Let's say that we're moving from A to B. All right, so we're moving from left to right. Here, my delta V is equal to negative of the EMF. I imagine that there's like a slide here, and electrons are coming along here with a lot of energy, and then they slide down. They say, wee! They slide down the slide, and they lose energy. Right? And it sort of looks to me like it's a slide, the way the battery is set up. Right? But I always think of that. If that helps you, great. If not, that's fine too. All right? But if I'm moving from the high potential side to the low potential side, I have a negative change in potential. If I'm moving from point A to point B, here my electrons are coming along and they just have a little bit of energy, or not much at all, and then they come up to the battery and they go whoop in energy. So here my change in potential, which remember, potential is just a measure of energy per charge. My change in potential is the positive of the EMF. All right, so let's put that in words. So for resistors, when you are traveling with the current, the change in potential is negative. All right, that is like this scenario. I'm moving from point A to B. The current is also moving from point A to B. If you're trying against the current, the change in potential is positive. That is like this scenario, moving from point A to B, but the current is flowing the opposite direction. These are all just sort of rules. They don't necessarily mean anything physically right now, but they're going to help us when we apply the loop rule and the junction rule. But if you don't get these little rules incorrect, then you won't be able to apply those correctly. So, all right, now for batteries, when you have your charges, I say electrons, but you know, we know that it really means protons. When you have electrons traveling from a low to high potential of the battery, the change in potential is positive. The electrons have gained energy. Remember, for a battery, this is like moving along here, and your electrons gain energy. All right, the energy of your charges increases. When you have electrons traveling from high to low potential, the change in potential is negative. The electrons have lost energy. All right, so that would be like, for example, having a battery set up like this. The electrons come along here, they have a lot of energy, but then they lose it. All right? When would you want to do this? When would you want to cause electrons flow from high to low potential in a battery? Why would you want to have a scenario set up like this where you have electrons going into a battery, losing energy, and then coming out the other side with less energy than what they began with? Well, simply, you want to do that in rechargeable batteries, for example, because there you will take electrical energy and convert it into, you'll take electrical energy and convert it into chemical energy. It's not even how you spell rechargeable. I'm not sure. Does it have an E in it? Look, I just sort of squeezed them together, so you could either say that it's EA or just an A. Rechargeable batteries. And rechargeable batteries, these convert electrical energy to chemical energy. All right, let's try this quick test. What you want to do here, I'm going to help you out just a little bit. What you want to do here is first pick a direction for the current. Doesn't matter what the direction of the current is. You just want to pick a direction for the current. If you pick it incorrectly, we'll see how it comes out. But you're going to say, well, I'm going to say that my current, actually, you know what? I'm going to say that the current flows the opposite direction. I'm going to say that the current flows in this direction. I'm going to work through this for you. Say that the current flows in that direction. All right. Then I pick a point in the circuit, say here, for example, and I pick a direction to travel. I'm going to travel with the current. It doesn't really matter. You can go with the current, against the current. You can choose the current to be in the direction that I've chosen here, or you can choose it to be the opposite direction. Let me show you, however, that the reason I chose this is because I know this is the incorrect direction for the current, because I know that this 18-volt battery is pushing current in that direction, and this 12-volt battery is pushing current in that direction. But since the 18-volt battery has more energy, it's going to win out. So by pairing these two batteries in this way, I effectively have a 6-volt battery that's pushing current in a clockwise direction. But anyway, doesn't matter which way I go. So I'm going to choose the current going in this direction. So here, I'm going to go through, and I'm just going to sum up all the potentials. I'm going to apply the loop rule, and that should equal to 0. So my first one here, I have negative I times R. That's negative I times 1 ohm. Here, I have a positive change in potential, so I have plus 12. Here, I have minus 2I. All right, that's 2 ohms times I. And here, I have a negative change of potential. See, my electrons come along here, and they go down the ramp, and they lose energy. And then coming up here, I have minus 6.6I. And then that's all equal to 0. And then I would solve this. It's going to be negative I, negative 3I, negative 9.6I, minus 6 equals 0. Okay. I'm going to let you go ahead and solve for I. Notice that your I will come out negative, and that means that we chose the direction for the current incorrectly. We'll see some more examples of that later. But we will pause this now and pick up with another multi-loop circuit soon.